Yeah, hello everyone. My name is Marc Fassbender. I'm one of Mark Hennington's PhD students at the University of Ottawa, and I originally come from Germany, where I did my MSc and my BAsc. I'll be talking about the geochemical signatures of Mafic and Felsic rocks in modern ocean settings and their implications for Archean greenstone belts. And I generally use geochemistry, petrology, and machine learning for that. First thing first, thanks to all our research partners and funders and financial institutions from Canada, obviously, but pretty much from all over the world. A quick outline for this talk. So I'll be talking about geochemical signatures in modern ocean settings, and if we actually can systematically identify signatures in certain lithotectonic environments. And if that is possible, if we can apply those systematics somewhere else. And if that is possible, if we actually can apply those techniques in the Abitibi greenstone belt. So that's part of this talk here. Some upcoming work that we are currently doing is identifying age relationships as well. So we want to see if age relationships, so using argon dating in modern ocean settings in the Laurel Basin, which you have seen before, are actually comparable to some extent to Archean environments. I'll be starting with Felsic Volcanic rocks. Why? Because Felsic Volcanic rocks have quite extreme geochemical signatures. That just simply makes it easy for me to identify end members. The other reason is we have much less Felsic Volcanic rocks as we have Mafic Volcanic rocks. So less data, which is easier for me to actually go through normal petrological workflows to identify signatures. But the third reason is, and that's actually the most important reason, is that Felsic volcanic rocks have huge implications for VMS deposits. They have been a major proxy to identify VMS deposits, ultimately resulting in the F classification from Lesher and from Hart et al. So that's the F classification. There are three main F classes, F1, F2, and F3, and that's based on the idea that F1 that it monitors the depth of the melt source. So F1 is basically a deep melt source, which is associated with high pressure mineral phases, such as garnet or amphibole, which preferentially incorporate HREs, and that results in steeply dipping RE pattern. F2 is a bit more intermediate, and F3 is the other end member in shallow melt sources. So now we do not have any high pressure mineral phases, so we will have flat RE pattern. It's also important to mention that we have two end members here, F3A and F3B. F3A can be pretty much found all over the place, and F3B is a particular HRE-enriched signature, which is very much uniquely tied to Archean environments. So one of the questions here is as well if the F classification is actually holding up, or if it can be applied in modern ocean settings as well. And for that, we compiled a database for Felsic volcanic rocks in modern ocean settings, comprising various lithotectonic environments covering ocean islands, ridge hotspot intersections, interoceanic arc and backup environments, and intercontinental arc and backup environments, resulting in more than 2,000 samples that then have been filtered for a certain set of desired elements. And those elements have been chosen based on their usage in lithotectonic discrimination diagrams, and obviously their ability and availability in our data set. And that resulted in 645 samples that we used for our analysis. And we started with a simple classification. So you have seen the test diagram before with the Si2 on the x-axis and sodium potassium oxide on the y-axis. And we can see that samples from the ocean island and ridge hotspot intersections tend to plot at the higher potassium oxide and generally have lower Si2 concentrations, and samples from interoceanic arc and backup environments generally have slightly lower Si2 concentrations, and they are more tholeiitic. Intercontinental arc and backup environments generally have high Si2 concentrations, and their sodium potassium oxides are quite variable. For comparison, plotting them in Winchester and Floyd, we see similar trends. So ridge hotspot intersection samples and ocean island samples generally have higher niobium-yttrium ratios, while interoceanic arc and backup samples have generally lower niobium-yttrium ratios, and intercontinental arc and backup samples plot right in the middle. And those general geochemical affinities are reflected in their trace element pattern as well. So we see that we basically have four huge end members. Samples from ocean islands, like from Hawaii or Samoa, which have a steeply dipping RE pattern. They have positive zirconium hafnium anomalies. And then we have ridge hotspot intersections, samples from the Azores and Iceland, which have very much this similar geochemical signature, but they have a much stronger negative europium anomaly. Then we have samples from mid-ocean ridges, which have a flat RE pattern. They do have a negative europium anomaly, and they lack, or they have very weak negative niobium tantalum anomalies. And fourth, our last end memory here, are samples from arc and near arc volcanoes, which have strong negative niobium tantalum anomalies, mostly flat RE pattern, and they basically lack a negative europium anomalies. So you've seen that quite a lot now before. That's obviously the Auer basin, and we have a few, not at all of those spreading ridges or in spreading centers, but at least a few felsic volcanic rocks at those locations. So we have them in the Volofar, we have them in the central Laos spreading center. Let me get the pointer here. In the NWLSC, MTJ, and close to the NDLSC up here as well. So, and you have seen that plot as well. So looking at the spider diagrams or multi-element diagrams here, we have quite a range of geochemical signatures. So samples down here at the Volofar have strong negative niobium tantalum anomalies. They have flat RE pattern. They basically lack negative europium anomalies. Same is true for samples up here from the Neo-Tubetao volcano and Neo-Tao volcano, but with differences in terms of their overall RE concentrations. And then we have samples from the Central Laos Spreading Center, NWLSC, and MTJ. And those samples basically lack negative niobium tantalum anomalies. They do have negative europium anomalies, and they generally have flat RE pattern. So we have quite a spread of geochemical signatures here. So to investigate the underlying systematics for that, we performed a principal components analysis. And principal components analysis, or short PCA, is nothing new. It's been around for quite a while now, but it's quite helpful and it's very successful to use it. What it does, it's a data transformation technique, and it breaks down the whole data set based on principal components. And each principal component reflects one element. So there are always as many principal components as there are elements in a data set. So in our case, we have 13 elements, hence 13 principal components, of which the first principal component reflects the largest variance in the data set, and the last principal component, the least variance in the data set. And then we have those red labels here. Those are loadings. Basically, the closer one of those samples plots to one of those loadings, the stronger this sample is actually affected by it. The important part here is, however, that we can see there are some trends here, right? We have in the upper left corner a bunch of ocean island samples and ridge hotspot intersections. In the upper right corner, we have mid-ocean ridge samples. In the lower right corner, we have interoceanic arc and back arc samples. And in the lower left corner, we have intercontinental arc and back arc samples. So there are some trends, which we want to verify using clustering as well. So what we did here is agglomerative hierarchical clustering. That clustering technique at the beginning assumes that each of those samples forms its own cluster. Then distances from one sample to another sample are calculated, and the two closest samples are incorporated in one cluster. Then the analysis is performed again, and the next level of two closest samples are formed in one cluster. And that procedure goes on and on until all samples actually contained in one final cluster, which in the end gives us a data tree from which we can decide how many clusters, geochemical clusters in that case, are representative for our data set. And that's 9 clusters here. And they pretty much fall on the same line here. So we have C1, C2 reflects ocean island samples and ridge hotspot intersection samples. C3 contains mid-ocean ridge samples. C4, 5, 6, and 7 contain interoceanic, or mostly interoceanic arc and back arc samples, and C8 and C9 contain intercontinental arc and back arc sample. And most of these clusters are actually a mixed bag of results, or mixed bag of certain lithotectonic environments, except cluster 3. So cluster 3 contains all of the mid-ocean ridge samples and a few mid-ocean ridge-like samples. So coming back to the Lao basin, those samples come from the CLSC, from the MTJ, and the NWC up here. Of which particularly the NWSC has a very strong mid-ocean ridge-like geochemical signature. In fact, it's basically identical to true mid-ocean ridge samples. The only real difference between a true mid-ocean ridge sample and the samples from the NWSC is that the samples from the NWC have the potential to be preserved in the geological record, whereas any true mid-ocean ridge sample will undergo the subduction death at some point. So it will be lost in the geological record, and our geological record is obviously biased. So plotting those samples again in the F classification, we see similar trends. We can see that samples from ocean islands, for example, tentatively plot rather in the F1 area. Same is true for samples from the ridge hotspot intersections, while samples from interoceanic arc and back arc samples mostly occupy F2, F3, and F4 fields. However, a few samples from mid-ocean ridges and those mid-ocean ridge-like samples are actually plotting close to or within the F3b array, which is mostly tied to Archean environments. So for comparison, those are a few samples from the Kamoskosia area from Kidd Creek and Metagamy, and while they have quite a significant spread, all of those are usually associated with F3b environments. However, this is obviously a plot and there's quite some spread, so we wanted to quantify those similarities. Which brings us back to applying and using random forest. So what we did now is we wanted to make our identified similarities somewhat quantifiable. So random forest is a machine learning algorithm which is basically, it's a classifier. It's trained on those 9 target classes here, and it tries to identify those target classes elsewhere. And by training, I mean this is an iterative process by which random forest learns which values are most meaningful to achieve the best classification outcome in the end. And it's not a black box, can be investigated, and in the end we are receiving percentages. So if a sample is very much alike C3 geochemical signature, then we are receiving that on a percentage, like 90% similarity here, or 20% similarity if there's basically no similarity. So we have that, and we applied that in the epitopic greenstone belt, and that very much confirmed previous things that have been postulated about the epitopy before. So we see that Naranda, for example, is quite a complex area, mostly related to back arc environment geochemical signatures. Kidd Creek, for example, is strongly associated with target class 2, which is the target class that is associated with ridge hotspot intersection samples. And we have samples from Metagamy, which are which have been classified here as target class 3, which is the target class that contained all of the mid-ocean ridge-like samples. But the obvious question remains, we have only a few Felsic volcanic rocks that we actually used in that database here, so what about the Mafic volcanic rocks where we have much more data? And that's exactly what we did. So we once again compiled data from ocean settings. We're covering the same lithotectonic environments, but now we do have more than 5,000 samples. We filtered that database again based on desired elements, based on their importance to identify certain lithotectonic environments, and that resulted now in 2,875 samples. We classified them as well, and now the problem becomes pretty obvious. So there are still the same trends that we have seen in the Felsic volcanic rocks, namely ocean island samples, for example, having high sodium and potassium oxide concentrations, but the spread for interoceanic arc and back arc samples is quite a lot. So we plotted them in the Winchester and Floyd as well, seeing that once again the trends are confirmed. Ocean island samples, for example, have high niobium-yttrium ratios, while interoceanic arc and back arc samples are plotting at the lower niobium-yttrium ratio trend. So to spare you seeing 3,000 samples in a multi-element diagram, I just summarized the end members here. On plot A, or I can just use that one, you can see the whole range of mid-ocean ridge geochemical signatures. So they have slightly dipping or depleted mantle signatures. They basically lack any negative niobium tantalum anomalies signatures. And in a Pierce lithotectonic discrimination plot, all of them plot in a strong linear array from depleted morph upwards to OIB-like geochemical signatures, except a few samples from Iceland. Then we have the other end member, which are samples from arc-related environments. So those samples do have strong negative niobium tantalum anomalies. Those samples also are mostly depleted, because those are mostly depleted, and all those samples are actually plotting in oceanic arc field, or close to or within the oceanic arc field. And I just plotted a few mid-ocean ridge samples here for comparison. And then we have those samples up here, which I would call atypical arc-like geochemical signatures. So those samples plot close to or within the continental arc field, or between the E-morp field, so enriched mid-ocean ridge-like geochemical signatures. And all those samples have weak negative niobium tantalum anomalies. They have slightly dipping RE pattern, but more important, they occur systematically in certain geological settings, which we will be talking about, or I will be talking about in a few more minutes. So now coming back to the Lao Basin, and we don't have the problem that we had before for the Felsic volcanic rocks, where we only had a few samples. Now we basically have more than 1,000 samples in the Lao Basin, which is absolutely helpful, because this is one of the best explored submarine environments that exists nowadays. But obviously, the geochemical signatures, which have been already complex for Felsic volcanic rocks, are even more complex for the Mafic volcanic rocks here. So that's the reason why we are using trace element geochemical ratios, right? So I've plotted here barium over Ytterbia, barium over niobium, and thorium over Ytterbia. And all those are frequently associated with subduction-related regimes. And I also plotted niobium over Ytterbia here, which is associated, or which is interpreted to interpret mantle enrichment. And they work perfectly fine, actually. So in areas like down here at the Volofar and ELSC, we can see that barium over Ytterbia, barium over niobium, and thorium over Ytterbia have or show the same trend. All of them are actually decreasing with distance to the slab, which is exactly what we expected. And now we are going up here in the northern Lao Basin, closer to the NELSC. And now we do have opposing trends. So while barium and over Ytterbia and thorium over Ytterbia have increasing geochemical ratios with distance to the slab, barium over niobium shows actually decreasing geochemical ratios with distance to the slab. So Marc, Alan, and Chris actually did a great job to tell you that this is a very complex area up there. But to be honest, it doesn't get much simpler than that, right? Because we know everything about that area. We have seen the structures, we have seen stress regimes, we can even monitor plate movements using GPS. We do exactly know where those samples come from, and still this is a very complex area. So geochemical ratios they are great, but they have to be investigated with care like anything else. And that's in that case why we went back to our principal components analysis and to agglomerative hierarchical clustering here. So I plotted those on 4 plots here. It's still one system, it's just for making the visuals easier. We can see, this resulted this time in 7 clusters instead of 9, and PC1 and PC2 are still representing most of the variance in the given data set. So samples that are associated with morp-like affinities are plotting in C1, C2, C3, and C4. And that is basically a trend from depleted morp, normal morp, enriched morp, towards OIB. And then we have samples that are plotting or occupying cluster 5, 6, and 7. And all those samples, or most of those samples, are interoceanic arc and back arc samples. So in summary, what we see here is that PC1 and PC2 very much reflect dry melting versus wet melting for PC2, and for PC1, which reflects source enrichment. So from enriched mantle sources, OIB-like sources, towards depleted mantle sources like depleted mid-ocean ridge-like samples. You've also seen that plot before. And now so what we did here is applying our clustering in the Lao basin. And what we see is that samples from Peggy Ridge, for example, and the CLSC, those are actually associated with depleted MORB geochemical signature, which is perfectly fine. Then we have samples from the NWLSC and the RR that Marc mentioned before, and those samples have normal MORB towards enriched MORB geochemical-like signatures, which is also expected because we have seen just from Marc that there's the Samoa mantle plume up in the north here, so enriched mantle source, which affects the whole northern Lao basin by enriched mantle components, including the NWC and the RR. Then looking at the Funnelar spreading center, we have they are mostly occupied by target class 6, which is the target class mostly representing strong hydrothermal fluid flux melt components. MTJ kind of mixed bag of results, but we have that's due to the tectonic environment there and the amount of plate boundaries. So we have mid-ocean ridge-like geochemical signatures and very close spatial distance to arc-related geochemical signatures. And then we have samples from the NELSC, which is target class 7, and target class 7 is associated with enriched mantle sources and fluid flux mantle components. So the story could be done here by just saying, okay, the Samoa mantle plume is the one to blame, but that is not the case. As we've seen from Marc, there's a high helium isotope ratios for that area here, but actually those areas here are not affected by the Samoa mantle plume. They lack that helium isotope geochemical signature. They lack that signature as well in terms of neodymium isotopes, strontium isotopes, and lead isotopes. So there's another component that's actually enriching that mantle up there. And Chris briefly introduced that, and we think that toroidal mantle flow can partly explain that. So what toroidal mantle flow is basically is we have a subducting slab, and around that subducting slab, due to subduction slab retreatment, mantle is actually flowing around the edge of that slab, and this mantle flow in models has a strong upwelling component. So what it does, it comes around that slab, and then it's penetrating the back arc from below, and that mantle is undepleted, so it's rather enriched. So we have different mantle components here that are coming together. We have the fluid flux component, we have that component coming around that slab, and we have normal depleted asthenospheric mantle from close by spreading centers. So what we did as well, what we have done before, is we applied random forest. So once again, our random forest algorithm has been trained on those 7 target classes, and it has been applied on the Abitibi greenstone belt here. And it kind of confirms the same trends that we have seen before. To make things easier, we just summed here a wet mantle component, or basically wet mantle component versus a dry mantle component. And we see that areas like Noranda, for example, are stronger associated with wet melting regimes, while areas like the Timmins region, for example, are stronger associated with dry melting regimes. So in summary, what we wanted to show here is that back-arc environments such as the northern Lao basin are quite complex. They are much more complex than we thought before, and they are important settings for preservation, most likely. Some of the geochemical signatures that we see here, like HRE enrichment in Felsic volcanic rocks, have pretty much strong similarities to geochemical signatures that we are actually seeing in the Abitibi greenstone belt. We also confirmed similarities that have been mentioned before, like the Noranda to the Manus basin, for example. But we also really want to highlight that in a complex microplate mosaic, like the northern Lao basin, where we have multiple spreading centers partly overlapping each other, that those areas are actually producing quite an unexpected amount of geochemical variability. And that being said, we expect that in the upcoming future we will investigate, or we will see, actually more similarities, because when you are going for and you want to dredge samples in the sea, you always go, or at first you always go for the big back-arc regions like the CLSC that you've seen the central part, or the Valofar, so the huge back-arc spreading centers, which are great. Loads of them have hydrothermal vent sites, so the biologists are in the books as well. But most of the time those areas are quite simple. But areas like the northeastern Lao spreading center are way more complex, and especially if you're going off axis, you will identify lots of geochemical variability, which statistically, if you compare that to the amount of samples that you have from normal back arc spreading centers, seem to be outlier, but they're actually not, and that is my main takeaway here. So thank you very much. No, we centered log transformed the data prior. Yeah.
Okay. And how much variance is accounted for in the first two principal components for both the Felsic and the Mafic?
I think I plotted that. So it's around 80%, I believe.
Okay.
Yeah, so that's 45 and 31 for the Felsics.
And which clustering methods did you use?
Agglomerative hierarchical clustering. Yeah.
Thank you. Very nice result.
Thank you.
Yeah, so you're using random forest training a model. The outputs of when you're testing it on ABT, you are basically conditioning the response to your training, which is the law base.
Yeah, that's correct.
It would be more interesting to add, in addition to that, some other different environments so that you are not biasing
Yeah.
your interpretation.
No, it's correct. What it does, what it can is identifying similarities, as you mentioned. What it cannot identifying basically differences. But as I said before, we are getting a quantifiable output. So, for example, areas like in render, for example, we are getting a certain percentage, like it's a likelihood of 70 or 80% that this sample actually has similarities to, let's say, the Manus basin. While areas for like Shibugemu, for example, have a very low percentage. So those areas cannot be classified using random forest from modern ocean settings. They must be something else. So we can't say what it is. We can only make comparison to what we know from modern ocean settings.